Good morning from Beijing, and also good morning / afternoon / evening for everyone joining us from places over the world. Welcome. This is the pre-event webinar for ICANN APAC DNS Forum 2023. My name is Chao Yilu. I am a postdoc at Tsinghua University, and I'll serve as your moderator for today. So, as you may have seen from the agenda, the theme of our session is DNS operation and challenges up on the cloud. So we came up with this topic because it is what's happening, the DNS meeting the cloud, if not perfectly sometimes. Whether you're domain holders, network operators, or just ordinary internet users, we might have enjoyed a lot of benefits. We don't need our own infrastructure for the DNS, just put everything onto the cloud and it'll start working automatically. But there have been challenges worth some discussion, like novel attacks, operational complexity, service centralization, and possibly more. So over this topic, we are very glad to have 4 distinguished speakers with us today to share their inspirations and thoughts over good practices. And thank you for joining us. And before we start, special thanks to Qi-Anxin Group, Alibaba Cloud, and the InForSec Forum for leading this session. And also we appreciate support from folks at ICANN, especially Alexis Liu, our person in contact, for making this possible. And finally, for our online participants, if you've got any questions for the speakers, may I suggest that you type them anytime into the chat box of Zoom. And after each presentation, we'll have about 5 minutes for questions. And when you type questions, please use the format #question to begin with your questions so that we can distinguish from other regular comments. Okay, so that's it from me. And I shall now introduce our first speaker, Jan Schallman, joining us remote from New York. Jan is a distinguished infrastructure security architect and adjunct professor of computer science with more than 20 years of experience building and securing high availability service at internet scale. His talk about the GTLD's new clothes, a look at centralization in naked domains, which is the 3rd edition in his series of research over service centralization. And now I'll give the floor to Jan, please, whenever you're ready.
All right, thank you very much. I just started sharing. Let me just know if you can hear me and see me, and if you can see my presentation.
Yes, you're doing great.
Okay, great, wonderful. So hello and greetings from the past over here in New York City. My name is Jan, and I've been working in information security / infrastructure architecture at various companies like Twitter, Yahoo, and now at Akamai, where I've seen my share of internet traffic, as well as the impact the concentration of data traffic can have on the health of the internet. I was honored to be invited to give a talk here at the APAC DNS Forum pre-event. And while unfortunately I can't be there in person, I'm excited to communicate remotely with all of you living in the future over there. So if any of you have any stock tips or sports results they wish to share, let me know. Anyway, the topic of my talk is the GTLD's new clothes, by which I mean to present my findings from analyzing the degree of centralization of so-called naked domains. Now, as you all know, and as I've myself noted before, it is illegal to give a presentation in the tech sector without using at least one XKCD cartoon. So let's get that out of the way. You may have seen this before, and as attendants here at the DNS Forum, you all know that yes, it's always the DNS, right? Now, with that out of the way, here's my current hypothesis. Despite being a network of networks, and famously distributed, designed to be decentralized, it seems that the internet is effectively and perhaps even increasingly centralized, with a fairly small number of companies controlling significant parts of the infrastructure. And with the DNS being the foundation for so much of what happens on the internet, we should be able to analyze the data from the DNS to support or contradict this hypothesis. Now, there are many different aspects that we can look at, and in the past I've done some research in this area. Specifically, last year, I started by looking at the distribution of the authoritative NS records in use by all the different domains. And I presented my findings at the ICANN DNS symposium last fall. You can find the detailed write-up in that URL there. The QR code also takes you to the same site in case you don't want to type it out or snap a picture of the slide or whatever you prefer. Anyway, so what I found there showed that there is indeed a fair amount of centralization with respect to name servers and their IP addresses, with over half of all domains NS records being served from just 4 autonomous systems. After that analysis, I then took a look at the distribution of MX records and found similar results. Over 60% of domains outsource mail to just 3 companies. Now, this isn't particularly surprising because, as we just heard in the introduction, the use of the cloud is super convenient, right? And we see cloud and infrastructure service providers grow, and of course, people take advantage of that, which then leads cumulatively to a significant concentration of power in those companies. Again, there's more details in that write-up that you can visit on my blog post there. After that, I'm an InForSec nerd. So of course, I also looked at CAA records, the DNS records used to grant certificate authority authorizations for, your web PKI effectively. And even though only a very small number of domains utilizes these records, they are again highly homogeneous. And so having seen all this from these 3 different angles, I figured, okay, what other data can we take a look at? And it seemed to me to make sense to continue and start out with so-called naked domains. Bare domains or naked domains, as I'm sure you all know, is really nothing more than, well, domains. They're second-level domains, to be more specific, although sometimes you may also hear the term APAC domains. That is, we're simply looking 1 level below the top-level domains. Now, any second-level domain necessarily must have some resource records, right? At a minimum, there's the start of authority record, as well as 1 or more NS records. And for any domain that's DNSSEC signed, we also get a few additional records. And the analysis of those might be another project for another presentation. But we also frequently find A or quad A records at the apex. And so this can be useful for SMTP to allow a mail server to deliver a mail in the absence of an MX record. But on the other hand, it's also much more frequently used in an HTTP context. So collaboratively, we've trained users to type www.example.com, right? But users are lazy and they find us annoying. And of course, in English, it's a really long word to say www, so people prefer to not do that. Users don't even see a distinction between the World Wide Web and the internet. So they basically leave off the www at the beginning and simply enter example.com into their browser and still expect to be taken to the company's website. And so for this reason, a domain may want to simply add an IP address or multiple IP addresses to their second-level domain name and create such a naked domain. So I was wondering, how many companies are doing that? And what addresses do they use? So to analyze that, I started out with about 1,200 data sources. I began with the GTLD zone files, which are available from ICANN centralized zone data service, which is super useful. I was denied access to one domain despite submitting the information they requested multiple times, and there's still a handful of domains that are still pending and have been pending for a few months, but okay. That is great. That is really, really useful data that you can get a lot of information out of. But of course, we have more than just the GTLDs, right? We have the country code top-level domains, or CCTLDs, and unfortunately, there are no requirements that mandate public access, and each country manages them however they see fit. That makes it really difficult to gain access for research purposes and explains why are there data brokers selling the partial zone data sets that they gain from DNS monitoring. Anyway, I reached out to all the operators, or rather all the operators where the whois information was correct and the contact address didn't bounce. Several operators do make their zone data available. Some of them, for example, using AXFR requests, while some others don't provide the raw zone data, but they do provide the names of the domains they have registered. And finally, we have two of the older original domains, ARPA and Gov, which also provide public access. And so with about 9 gigabytes of compressed zone data, I figured might just quickly do a few DNS queries for the various records, because how many could there possibly be? And I also do reverse lookups and resolve CNAMEs. And after a few hours, my local bind ran out of memory, fell over. I started hitting my ISP's resolver with hundreds of thousands of lookups in the .xyz domain, and they quickly shut that down and locked my virtual private server. Anyway, what I'm saying is I learned a fair bit about tuning bind and eventually got my local caching resolver to not choke. Then parsing out the results, I ended up with roughly 240 million domains. About 70% of those, 166 million domains, are in .com alone. So it's like a huge chunk of that data set. And I looked at the distribution of IPv4 versus IPv6 addresses on those naked domains. Now, DNS data is necessarily always a snapshot in time. And during the lookup, there are many things that can go wrong, which is why you see over here a fair number of NX domain and survey results. But those aside, we find that about 9% of all domains, or 24 million, do not have A or quad A records. 2/3 of all domains are IPv4 only, with only a measly 8.5% being dual stack, and IPv6 only is so small it isn't, barely worth mentioning. But not all domains are of equal importance. So in addition to just looking at all of the domains, I also ran the same analysis for the top 1 million domains as ranked by, in this case, the Tranco list. Here we see that things are a little bit better with respect to IPv6 support, meaning that among the popular 1 million domains, we have almost a quarter supporting IPv6. So yay, IPv6. One thing that is not shown in these charts here is that aside from having A and quad A records, there are also a lot of naked domains that have CNAMEs. And that is, the actual second-level domain name has a CNAME record pointing to another domain, which then may resolve to an IPv4 or IPv6 address. And of course, having a CNAME record at the apex is against RFC 1034. Because as a second-level domain, there must already be at least an SOA and an NS record, right? And RFC 1034 says, thou shalt not have a CNAME in the presence of any other resource records. Except, of course, there's also RFC 4034, and DNSSEC ruins everything by saying, no, wait a second, you can have other RRs next to a CNAME, because otherwise DNSSEC won't work. But anyway, you still can have a CNAME at the apex. Only many organizations really want that. And for the most part, the world doesn't end, because many systems are tolerant in what they accept. But either way, so I went ahead and looked at where those CNAMEs point to, and found that there's a fair bit of clustering here too. So over half of all the CNAMEs encountered at the apex points to this one domain here, the rather aptly named tref1.hugedomains.com, with other sizable representation by other domain name registrars, domain name monetization companies, and the like. This is the same data, basically. It's just in pie chart format, because pie, who doesn't like pie? But let's go back to the IP addresses. NX domain, serve fail, and no data aside, I found around 201 domains that did have at least one IP address. 201 million domains, rather. And of course, it's not uncommon for a domain to have more than one IP address. So for the small number of domains that are dual stack, it's quite common to have an equal number of IPv4 and IPv6 addresses, for example. But there are also domains that have quite a few more IP addresses. For example, there are 236 domains that have over 100 IP addresses, which may seem excessive. But of course, when you make a few 100 million DNS lookups, you find all sorts of funny things. So here's the list of the top 3 domains by largest number of IPs. There's vanao.com with over 2,000 IP addresses, mikaclay.us with over 1,000, and kijanigarage.com with over 700. If you do a lookup right now, by the way, you may find that there are different numbers. The data is in flux, as I mentioned, and also seems just in general that somewhere somebody went overboard in trying to do a DNS-based round-robin load balancing over all these IPs. But you should find that you get back, huge data packets with hundreds or thousands of IP addresses back. And talking about finding funny things in the data, well, guess what? There are almost 700,000 domains that use reserved IP addresses in the public DNS zone data, right? So for example, there are over 500,000 domains that use a loopback address, and 35,000 use an RFC 1918 address. And yay, you get an extra free XKCD comic. So most of those RFC 1918 seem to like 10.10.10.10, 10.0.0.1, and 192.168.1.1, but you see like a real range of all the other ones as well. There are 31,000 use of the current network 0/8. There's use of RFC 6598 addresses for shared address space or carrier grade NAT. Of course, there's link local addresses. Why not? There's documentation IPs. You won't be surprised to see that now people started using the previously reserved Class E network 240/4. So we know that this is being discussed or being released into some degree. And yes, we do see this as well. There's use of the unspecified address. And of course, also some people use the limited broadcast address 255.255.255.255. But all that funny business aside, let's talk about which IP addresses are encountered most frequently. All in all, I found about 328 million A and quad A records, which mapped to about 13.7 million unique IP addresses. So that, of course, implies that many domains share an IP address, meaning they resolve their A or quad A addresses to the same IP address. And some IP addresses are found more often than others. In particular, I found that around 200 IP addresses are used by over 100,000 domains. And a small number of IP addresses are even used by over 1 million domains each. The top 3 most widely used IP addresses are 34.102.136.180, which is used by over 25 million domains. And 3.33.152.147 and 15.197.142.173 are used by over 9.8 million domains each. Of all of the top 20 most frequently IP addresses, again, we're seeing that they're all IPv4. So we're seeing, again, this concentration in IPv4, and IPv6 is really not taking off as much as we would like. There's only 8 IPv6 addresses in the top 100 most frequently used addresses. For the top 1 million domains, this looks similar. We have about 1.8 million A or quad A records in about 700,000 unique IP addresses. Now, obviously, the top 2 IP addresses here belong to the same organization, right? myshopify.com in this case. But it seemed like it might be interesting to see how the IP addresses, the ones that are frequently encountered, how they're reversing to identify the controlling domains. And so I went ahead and tortured my DNS resolver a little bit more to find out that we have about a little over half of the IP addresses do not have a PTR record at all, or they fail resolution. Of the remaining 6 million PTR records, I found that we have about 30,000 or so that actually are CNAMEs themselves in the in-adder/upper domain, which is specifically permitted by RFC 2317, but which was not something I had actually encountered before. So that was kind of interesting. The other thing that's perhaps not entirely obvious is that a single IP address can reverse to multiple domains. And so I found about 550 IPs that reversed to over 100 domains each. and the top 3 are being shown here. So what you see here is, and I think this is really interesting, is that there are some IPs that have a much, much larger number of PTR records than they are currently used for, which hints at the use as being for domain name parking or reuse, where like, the name was sold, removed, expired, and the PTR records in Internet Opera were not cleaned up, possibly. But now, looking at the names which IP addresses reverse to, we see again concentration across common providers, notably Amazon AWS over here. Although I thought that having PTR records pointing to the root was also interesting. At the bottom there are 5.7 thousand IPs that actually point to dot in Internet Opera. So as usual, whenever I notice that multiple things point to the same second level domain, I then go ahead and check if we can normalize all of the data that I have and determine what the common domains are. That is, we can add up all the different names that are under AmazonAWS.com and display the distribution, which then looks kind of like this. So we see about 32% of all IPs that do have PTR records point to AmazonAWS.com. 7% or almost 7% pointing to Google user content, and 6% pointing to secureserver.net, and so on. Secureserver.net, by the way, if you're not familiar, is GoDaddy's Wild West domains, effectively. But so these are the unique IPs. But it seemed we should weigh the IPs that are used by more domains a little bit more than those that are used only by one IP, right? So I started to take that into consideration. And I found that the most widely used providers we have here, we have almost 100 million IP addresses that are added up by frequency of use, reverse into only 20 host names, with the top 3 being, again, Google user content, AWS Global Accelerator in this case, and Wixsite, which apparently had a typo in its name, but probably couldn't go and fix it once it was so widely in use. So remember, kids, domain names are forever. Now, if we again collate the reversed names by domain name and not by FQDN, we see an even starker concentration. That is, we have 121 million IPs are reversing into only 5 different domains. Yeah, we have about another 500,000 or so domains that reverse to localhost, but that's just, you know, a little piece of information, a little nugget there. But let's look at those 5 domains here. You should again notice fairly quickly that, of course, AWS Accelerator and AmazonAWS.com are the same entity. And likewise, Google user content and 1E100.net are also the same entity. So that got me thinking as to how I can better identify IP address space concentration in use here. Now, visual inspection by domain name is not going to work well, and whois data is often unusable or not available. So instead, I went ahead and mapped the IP addresses to their autonomous system numbers. And there I found that the IP addresses of the top 1 million domains map into around 12,000 different AS. But of course, here too, we can see a high degree of concentration. Almost half of the top 1 million most frequently used IP addresses map into only 20 AS, with Cloudflare, Amazon, and Hostinger being the top 3 in this case. For all of the domains, those 328 million IP addresses that I encountered, 38% map into Amazon, Cloudflare, and Google's AS. So here's the breakdown of the most frequently encountered AS. If you look at this again, as before, we can also identify distinct AS owned by the same company. And so if we add those up together, that gives us this picture, where we see that there's about 4 organizations that control over 50% of the most frequently encountered IP addresses, and 10 different organizations controlling about 2/3. All right. I know I just went quickly through all this. I threw a whole bunch of numbers and pie charts at you, but let me try to bring this together with what I think this tells us. So for starters, and this may not be surprising, but it's still disappointing, we find that we're still very much in an IPv4 only world. Almost 3/4 of all domains are v4 only. We also saw that there's a clear demand for CNAMEs at the APACs. As I mentioned, this is something that people want, and especially CDNs have to deal with, as they want to allow customers to effectively load balance on the naked domain. Akamai, for example, uses a technique called zone apex mapping to get the equivalent functionality. Other CDNs have their own solution. In my opinion, there's probably a good room for a standardized solution here. But with respect to the initial question about the centralization of the internet, we did note that a single IP address is used by over 10% of all domains, which I think is quite impressive. We noted that 37% of the cumulatively encountered IPs reverse into only 5 domains, owned by only 3 companies. And that almost half of all domains IPs map into only 3 companies AS. So does this confirm the initial hypothesis? I think that combined with the other data and research I did, it does give strong evidence. However, it is important to know that the data is incomplete. The inability to get access to the CC/TLD zones means that our data is necessarily skewed towards the US market. For example, if I would expect that if there would be a significant shift in weight if I'd been able to analyze the .cn, .jp, or .de zones, to name just a few examples. Secondly, I want to stress that what I have presented here is only a snapshot in time. It might be interesting to track these findings over a longer time frame to see whether or not we are moving towards an increasingly centralized internet or not, meaning we would redo the same analysis periodically and see whether or not we see movement of larger numbers towards smaller numbers of organizations controlling them. Anyway, I think my time's up. This is what I wanted to present to you. I'd like to thank you for your interest. I'll be happy to answer questions here in the session if there's time, but you can also feel free to email me. My address is available there at the bottom of the slides. Thank you very much.
Okay, thank you, Jan. That was very impressive. And we've seen a lot of surprising numbers popping up. I see that there has not yet been any questions from the chat box. So do our on-site audiences have any questions? Well, actually, I personally have one. I'm very curious about the, you said that some domains map themselves to many IP addresses, some even over 100. I don't know if you have looked into the actual IP addresses, but I'm very curious about their intentions to set up these this many IPs in their zone files. Do you have any comments on this or insights?
I mean, it's difficult and I can only speculate, right? So one thing that I'm guessing is that people try to do some sort of load balancing by saying, okay, we want to have more IP addresses, so I just return a whole bunch of them. The other thing is that I think, I don't think I have it here in my slides, but I looked at them and the 3 providers or the 3 sites that have these really large numbers are offered by the same organization or map back to the same organization, which suggests to me that there's a registrar or a hosting provider that simply says like, hey, we've got lots of IP addresses. When somebody new spins up, we just put them on all of them. But it's not quite clear to me whether or not there's a misunderstanding of the performance benefits of the packet sizes that they're incurring here, how they're actually load balancing, or if it's just laziness where there's like, hey, lots of IP addresses, we just put them on all and then reserve it. I would have to look more into that.
Yes, and also from the technical perspective of the methodology, you've also mentioned that by setting these many IP addresses, the DNS packets may truncate themselves because their size is too large. Have you encountered any of the problems during your experiment?
Yeah, so I know that I ran these queries on my own server, which has its own caching resolver and doesn't have any problems. But if you run this, for example, on certain managed devices, there are a number of corporate firewalls, as well as management software that runs on endpoint protection services, that really choke whenever something fails over to TCP, or that truncate packets arbitrarily, right? So that is definitely, I would think, from happy eyeballs, from a user's perspective, I would expect there to be a number of problems for the end users, definitely.
Okay. Still see no coming up. Okay, any other questions? Okay, we have one on site. One sec.
Hi, I have a question. I noticed that many domains are centralized to several IP addresses, but you mentioned that most of them are IPv4 addresses. I guess that maybe the reason is because there are some popular DNS service providers that they use IPv4, but do you have any comments or any reasons that why IPv6 is rarely seen in this scenario?
Yeah,
I'm kind of curious.
Yeah, so I think that is somewhat surprising, because the most popular IP addresses are all offered by companies that understand and serve IPv6 very well, right? So we have Google User Content, AWS in particular, Wix, they all generally support IPv6. However, I think what is going on is that it's not that those companies are providing actually the service, but they're just the endpoint where they're hosted. That the actual hosting service, the one or the registrar, that where people register their domains, they may actually have as a default possibly IPv4 only, and that users would have to actually know to request IPv6. And some of the stock domain parking services seem to focus on IPv4 only, because all you need is have it registered, and then they may just have a parking site that they just go for IPv4. But I suspect that it's to a large degree the lack of defaults and the lack of users requesting it. If it was by default dual stack, there would be a much larger number, I'm sure.
Okay, thank you.
Okay, thank you. I guess that's yeah, I guess the time is running low. So yeah, thank you, Jan, for thank you very much for joining us. It's been yeah, it's been a challenging time zone for you. So yeah, just thank you very much for doing this, and we'll see you again soon.
Yeah, thank you very much for having me.
Thank you, thank you. Okay. So our next talk describes a new type of attack, disrupting the load balancing of authoritative DNS servers. There has been a change in speaker. Mr. Baojun Liu cannot make it, unfortunately, and we have Mr. Fenglu Zhang with us. He is also a lead author of this work. Fenglu is now a PhD student at Tsinghua University. His research interests include internet measurement and network security, and has published papers at several top academic conferences, including this work to be presented today. He's also a CTF player as a member of teams Redbud, Blue Lotus, and T Deliverers. And Fenglu, the floor is now yours. Can anybody online see the slideshow? Alexis, can you see it from your side?
Yes, it's up online.
Okay.
Okay, ladies and gentlemen, welcome to Silence is Not Golden, Disrupting the Load Balancing of Authoritative DNS Servers. I'm Fenglu Zhang from Tsinghua University. DNS provides critical services for mapping using user-friendly domains to IP address. Typically, a user queries a recursive resolver for a domain. Then, the resolver forward the query to a root server, TLD, SLD, and the domain's authoritative servers. The authoritative servers is delegated to provide the final results of the domain. Hence, it plays a critical role in domain resolution. As a result, DNS specification require deploying a load balancing mechanisms on authoritative servers. For example, RFC 1034 requires each DNS zone should maintain at least 2 authoritative servers. RFC 2182 further requires this NAND server should be geographically and topologically device. Nowadays, DNS hosting in cloud services is becoming more and more popular. Some well-known DNS hosting services, such as Cloudflare, Amazon, they provide infrastructure to support resolution of hosted domains. More importantly, they simply the complex work for customer to manage a domain. Another reason to utilize DNS hosting services is that they natively support load balancing mechanisms, which comply with the requirement of DNS specifications. Here is an example of a domain hosted in a DNS hosting services. A recursive resolver can witness 16 candidates while querying the hosted domain. So far, so good. However, due to the consideration of cost, assigning different authoritative server for each hosted domains is impossible. Instead, many hosted domains share the same set of authoritative servers. Consequently, load balancing is critical to the stability and the security of DNS hosting services. The outage of a DNS hosting service can affect numerous domains. In this study, we reviewed a new attack, disobedience, which can efficiently disrupt the load balancing mechanisms of authoritative DNS servers. Our comprehensive measurement proved that extensive target can be affected by this attack. Several mainstream recursive DNS software are exploitable. A considerable proportion of popular domains are vulnerable. Also, we observed the attacker could exploit numerous open resolver and several popular public DNS services. The security impact can be served once the attacker disrupts DNS load balancing. An attacker can bypass existing defensive mechanisms and overload name servers. Note that such overload is different from most traditional DOS attack. The attacker redirects legitimate DNS traffic to a victim instead of generating malicious traffic. As a result, the choice remaining for the victim are increasing hardware capability or ignore traffic from billion clients. Also, the attack can lower the bar of traffic hijacking and cache poisoning. The load balancing mechanisms provide multiple candidate NAND servers. which can be deployed on different location and AS. Disrupting the load balancing eliminate the probability for client to query diverse name servers. As a result, manipulation of DNS response become less challenging. Moreover, an attacker can also disrupt the infrastructure of DNS-based load balancing systems. Some implications directly configure each name server to respond with different sets of resources. Therefore, an attack against the DNS load balancing can subsequently impact the application servers assigned by name servers. Now, let's move to the disciplines attack. We observe a prevalent response strategy of authoritative servers. Silence is golden. In particular, they conflict not to respond to the DNS request outside their authority. While receiving a request for a domain outside of their authority, is slightly drop the request instead of returning any answer, such as refuse or NS domain. It is operator believe this is a great strategy against DNS application attack. However, such a strategy of authoritative servers can cause misunderstanding when a resolver meets a silenced authoritative servers. This is because the mainstream recursive software prefer the name server with the best performance and avoid the name server failing to respond. Worse, this status of name server is globally shared by all domains. Here is an example. We assumed an attacker asked the resolver to query an authoritative server for a domain that is not hosted on the server. The authoritative server silently drops the request and doesn't generate any response. Then the resolver consider the authoritative servers is down and record the status for the name server. Note that all domains globally share the status of name server. The next time, even a user query a hosted domain to the resolver will avoid querying to the fault name server and query other candidates. Such implementation caused the disability attack. Let me detail the attack with an example. We assumed the victim's configuration is this. The DNS hosting services assigned is its hosted domain to NS record, ns1 and ns2.com. Each NS record point to 2 sites of authoritative servers. In total, 4 sites of authoritative servers are assigned to a hosted domain, IP1 to IP4. As a result, when user query a set of hosted domain, the resolver will redirect the legitimate traffic toward 4 candidate authoritative servers. So far, so good. Now, we assumed the attacker wants to attack a single NS record, NS1. The attacker's configuration is stated here. The NS records of attacker's domain is set as NS2. Note that the attacker's domain is not hosted on the target authoritative server. Then the attacker requests the resolver to resolve his domain. According to the configuration of the attacker's domain, the recursive resolver turned to query NS2. However, since the domain is not hosted on the name server, it slightly dropped the request of the resolver. Consequently, the recursive resolver records the failure status of NS2 and lower its priority. This status of name servers is shared across all domains, including both attackers' domains and hosted domains. As a result, when a billion users query the hosted domains, the resolver avoids selecting NS2 and forwards queries to NS1. The load balancing of authoritative servers is disrupted. Also, the attacker can perform another variant and target a single IP address of authoritative server. In this case, we assumed IP1 is the victim, and the name server of attacker's domain is finally pointed to IP2 to IP4. After receiving attacker's query, the resolver turned to IP2 to IP4. The name server dropped the request, and the resolver recalled the failure of IP2 to IP4. When billion user query the hosted domain, the resolver forward the query to IP1, and the load balancing of authoritative server is disrupted. Now, let's move to the evaluation of this attack. We first evaluate explorable hosted domains, authoritative servers, and server providers. To this end, we conduct a large-scale measurement. We select the top 1 million SecRAN FQDN and the Chanco SLD as targets. Then we request the NS records at the private zoom for each domain, along with the IP address. Further, we mark a NAND server as vulnerable when it satisfies two conditions. It ignores queries for a domain that is not hosted and responds to its hosted domain. Our measurement results showed that about 23% of the top FQDN and about 4% of the top SLD can be exploited by disobedience. Zooming in the top 100 domains, the proportion of vulnerable FQDN and the SLD increased to 29% and 11% respectively. Several vulnerable domains are related to popular applications. For example, the API of a mobile operating system, short-form video applications, and e-commerce. Our results show that in the top FQDN, around 12% of authoritative servers were exploitable. This ability can also impact the popular services provider. For example, DNS Point, a popular provider affected by disabilities, is hosting a number of popular sites, including around 6% of top FQDN and about 1% of the top SLD. We then evaluate the application factor of disabilities, which means that the multiplier of the traffic load on victims caused by legitimate traffic. While targeting an IP address, the average AF is around 8 times and 7 times for the top FQDN and SLD. The maximum AS is 32 times and 46 times respectively. Interestingly, we find that domains requiring high availability suffer from a greater application impact since they are assigned more name server for load balancing. For example, the AFs reach 46 times for a vulnerable SLD owned by a technological company. We also evaluate the exploitable target from the side of the resolver. Here is the methodology. We select the recent version of 5 main-chain recursive DNS software. Then we conduct a white box analysis for open source software, and we perform code reviewing and dynamic debugging for them. Further, we evaluate the impact of disabilities through simulation. For open source software, we extract the essential code and execute it in a simulated environment. For closed source software, we run the whole operating system in the simulated environments. Our results show that three of the 5 analyzed software are vulnerable. Such vulnerable software is enjoying high market share. Unfortunately, we also observed that the efficiency of disabilities is quite high under different conditions. For example, during the simulation, we find that on average, vendor 9 sent about 6,000 legitimate queries to the target name server after receiving only 1 queries from the attacker. We further conduct an extensive measurements to confront how these billions affect real-world resolvers. We select about 40,000 stable resolvers and include 14 well-known public recursive services as our targets. Then we act as the attacker and the billion client to send queries to the target resolver. We established a set of vulnerable name server to receive the request of the test resolver and configure our own domains as attackers and the victims' domains. We found that about 38% of the tested open resolver are vulnerable. They are distributed in many countries, cities, and AS. The results indicate that the vulnerable resolver serves many users whose DNS traffic can be diverted by these billions. We also observed that 10 of the 14 popularly recursive services are vulnerable, including Cloudflare, OneDNS, and Frontline. Here is the discussion and conclusion about this study. We conclude that the rule reason causing these billions. From the view of authoritative servers, we discussed these issues with the affected hosting services. They confront that dropping DNS queries from non-authoritative domains is adopted as a defense mechanism to protect against DNS application attack. From the view of the recursive resolver, it decreases the priority of a name server when its query is timeout, and share the status of name servers across all domains to improve the efficiency of domain resolution. To mitigate the security issues, we believe that the authoritative servers should take responsibility since their strategy violates the DNS specification. RFC 8906 said that failing to respond at all is always incorrect. We suggest an accurate response for non-authoritative domains that follows the DNS standards, returning refuse with an eDNS error code. In the case that is not supports eDNS, we suggest returning refuse instead of other misstanding errors. This responses does not cause the DDoS attack since it doesn't generate more response packets than what attackers said. After disclosure, Tencent Cloud, Amazon, and the TSNS has taken action to fix these issues. We also believe adjusting the recursive software is far more efficient for fixing these issues since these software are installed on most of the affected resolvers. We recommend addressing these issues by adapting the strategy of node resolver. Although not share the status of name server across all domains, however, it tries other candidates with a certain probability and restores the status of a field name server once it responds successfully. After disclosure, all vendors of vulnerable software acknowledge our findings, but they insist that authorities servers should fix these issues. Here is the conclusion of this study. First, we uncovered a vulnerability that adversary could exploit to disrupt its functionality. Then we evaluate the real-world impact of our proposed attack. Finally, we disclosed issues to vendors with mitigation option. Tencent Cloud and Amazon had take actions to fix it. And here is the reference. Thank you for your interest in our presentation. Wish you have a nice day.
Okay, thank you. That was the presentation from Fenglu Zhang. Let's see if we've got any questions from online. Not yet. So we may take questions from our on-site participants. Any questions? Okay, then I'll raise one. Do you have any updates over the recent actions of the affected vendors, either recursive resolvers or authoritative service?
We did not trace their if they are fixed these issues, but in the recently contact with them, the software vendor considered these issues should be fixed by the authoritative server sides, and I think they won't fix this issue in the software. And some vendors of name servers have fixed these issues.
Okay. What about the cloud providers themselves? Has anyone taken steps to fixing this issue?
No, I haven't received this.
Okay. Okay. Anyone else online having a question? Alternatively, you can just raise your hand so that we can unmute you and we can chat interactively. Okay, not seeing any yet. So thank you. That was our second speaker. And now let's move on to the next one. Let's hear from cloud DNS providers themselves. And our third speaker is Yong Ma, a principal engineer of DNS development at Alibaba Cloud. He has multiple years of rich experience in security and stability of the DNS, especially cloud-based DNS systems. His talk today covers the challenge and practice of integrated cloud DNS. And I'll now hand the stage over to Mr. Ma.
Okay, hello everyone. I appreciate your time and attention today. I'm Yong Ma from Alibaba Cloud DNS. My colleague David Sung and I prepared this presentation. It's about the challenge and the practice of integrated cloud DNS. Okay, let's start. This is the agenda of these slides. Firstly, let me introduce briefly about Alibaba Cloud DNS. Then share our thoughts about the trend of DNS in the context of infrastructure evolution from the traditional IDC to cloud integrated, as well as the challenges and the practice associated with this transition. Finally, conclude with some takeaway points. It's a little slow. Just wait for a moment. Okay, so Alibaba Cloud DNS is a cloud-based DNS service and provides domain management and resolution services for business and individuals. It can seamlessly support public cloud, private cloud, and on-premise IDC. It offers a wide range of features such as customizable DNS records, enhanced security, and fine-grained schedule policy. The service also has a highly available and scalable architecture, providing both public and private zones. Take advantage of Alibaba Cloud's powerful infrastructure and technical platform. It's running on 27 regions globally, has more than 300 DNS resolve clusters. It manages over 100 million DNS records. Okay. Additionally, it carries about 2.5 trillion DNS queries per day, and more than half of these queries are internal DNS traffic in the cloud. Okay, next, let's look at the 3 stages of IT infrastructure evolution. So the first stage is based on the traditional IDC. In this stage, DNS and the communication technology component focus on the basic protocol, and it plays a connection-centric role. In the second stage, with the rise of cloud computing, IT infrastructure more and more are migrating to the cloud. And this stage, DNS and the basic service is deeply integrated with the cloud, providing rich functionality for various applications. It's showing an application-centric role. So the current evolution has reached the third stage, the cloud integration. It means bringing multiple cloud IDC environments together, either in a hybrid deployment or on the multiple public clouds. By this way, enterprises believe that they can obtain more self-controllability, heterogeneous resources, and cost optimization. In this stage, DNS should be able to integrate it with multi-platform, seamlessly manage DNS resource and service on different platforms. DNS is newly added management-centric role. We call the DNS service for this stage and the integrated cloud DNS. Next, let's take a closer look at the integrated cloud DNS. In the modern internet, with cloud, mobile network, and IoT, IT infrastructure and resources are integrated with both cloud and smart ends. The existing converged cloud concept focus on the backend resources. Differently, we have an end-to-end point of view, which includes client-side resource like the smart IoT applications, browsers on client side who do their own DNS. For example, let me give an example. All these things is come from our customers' requirement. So some large companies has customers worldwide. They usually deploy their IT infrastructure and service on multiple platforms. such as in Alibaba Cloud, its own IDC in China, and AWS abroad. They also want to use the new compatibility of DNS for applications such like HTTP DNS or DNS over TLS. They have many difficulties to management and integrate the different DNS service providing in different environment. So they need some they have some requirements such as interoperation among the different environment, security forwarding the query and answers, consistent resolving and scheduling functions, advanced type management platform. So based on these requirements, integrated cloud DNS emerged. It's a way to operate as a single cohesive security DNS infrastructure for an enterprise in cloud integrated environment. Okay, so now let's take a look at the main challenges in the integrated cloud DNS. So the first challenge is flexibility. With the enterprise application deployed on the integrated cloud platform, there are a variety of new scenarios and customized requirements for DNS. It requires adaptation to different cloud environments, operating systems, hardware architectures, and network configurations. And it also requires user-defined DNS resolve cluster division with different DNS records. For example, a company may develop in on-premise IDC and deploy production in a multiple cloud environment. Then it needs to create resolve clusters in these two environments. And the DNS resolution may use its own custom DNS records when development. While after online deployment, DNS resolution may use public DNS records. So in order to support this use case, integrated cloud DNS must be flexible enough to adapt to various platforms, easy to expand functions and manage multi-divisions, clusters, and DNS records. So the second main challenge is scalability. With the rapid development of mobile network and IoT, more and more terminal devices need to resolve DNS in a more secure ways to prevent privacy leaks and resolution hijacking, which brings fast-growing security DNS connections to the DNS service. We observed that the DOH and DOT traffic of Alibaba Cloud DNS increased by more than 20 billion queries per day in less than 2 years. And at the same time, the scale of DNS data is growing rapidly too, which also require a high throughput distribution system that can quickly and accurately distribute DNS data to resolve clusters in different environments around the world. The integrated cloud scenarios also brings a large increase in resolve nodes and needs to support a massive isolated tenants. All of this requires the integrated cloud DNS system to have high scalability to cope with various large-scale scenarios. So the third challenge is consistency. Integrated cloud DNS need to maintain the DNS records consistency in different clusters, regardless of whether it's in multi-cloud or traditional IDC, and keep consistency, resolve logical and scheduling strategy. Also need to ensure the integration and confidential DNS records during the entire process of data distribution and resolution. So the last main challenge in integrated cloud DNS is stability. Many traditional DNS systems are based on open source DNS softwares. But open source software has stability risks such as CVEs. So the integrated cloud DNS platform choose to use self-development DNS softwares. But self-development DNS software verification and testing also is a challenge, especially in rapid iterative development of functions. So in a large-scale platform, if there is one special packet can make the core DNS software crash, it will be a disaster. Okay, so and also in the integrated cloud, there are diverse infrastructures. They have inconsistent SLAs, so it brings uncertainty conditions. It's hard to design a stable system to meet all these different infrastructures requirements. And because the large scale infrastructure, it takes the challenge for the monitoring to the host DNS systems, and there are many. There are more and more different environments and software involved in these systems. So it takes the troubleshooting requirements, and we need to troubleshoot any issues quickly. Okay, so the next is about our practice. This is the practice of Alibaba Cloud DNS. I will show some key points. The first is we have a full stack self-development DNS software. By this way, we can meet our customers' continuous changing requirements. And we can break the limitation on the traditional DNS protocols, and with this way we also can avoiding the open source software risk. The second point is it's about our distribution system. We have a center to edge and a two-level distribution system. In the central distributor, it's based on a super high performance message queues, and on the edge side we have many edge distributors. It can pull data from the central distributor and distribute it to the DNS clusters with Raft protocol. By this way, we can achieve a very high performance. We can distribute users' changes into the resolve clusters around the world only in 1 second. And this system also have a very big throughput. It can scale to support 100. It can scale to support million DNS record changes per second. Okay, and the third point it's about the core components are fully heterogeneous. For example, we have two self-development DNS resolve software. These two software, the architecture, these two softwares architecture is totally different, and they are developed by different programming language. So by this way, we can deploy them into many different platforms. For example, if we deploy it on a physical machine, it can provide more than 100 million query per second, and we also can deploy it in the cloud native environment. It can seamlessly integrated with the cloud native system and dynamic scaling with his size. So the last point is our powerful operation and maintenance system. By this system, we can monitor the whole system, every resolve node's running status, and it manages all the configuration baselines. It includes IP address, software configuration, and the service node, and so on. And it also management our standard operation procedures for online changes. It can running this SOP automatically. So by this way, it can improve the operation efficiency, and at the same time bring at the same time reduce the risk of operation. And we also use AI technology in this system. By this technology, we can improve the decision making and problem resolving. Okay. It's okay. So finally is some takeaway points. The first one, based on our observation, internet DNS traffic in the cloud has surpassed the traditional DNS traffic. The second is DNS has a new role and challenges to support the new cloud integration deployment for IT infrastructure and E2E online service. And the stability, scalability, consistency, and flexibility are still key technology requirements for integrated DNS. So the last, the integrated cloud DNS is not a closed system. So strengthening the resilience and the security of DNS requires collaboration and cooperation between the private and the public sectors. Okay, that's all about my presentation. Thanks for your listening. Is there any questions?
Okay, thank you. And we're now, we have some time for questions. Check first if we have anything fine. Okay, it seems not yet. Turn to the venue. Any questions from our on-site participants? Oh, okay, yeah, fine.
So is there any new security problem about the integrated cloud DNS compared to traditional DNS?
Yes. there's a lot of new security problems. Because in the traditional DNS, the scale of the system is smaller than the cloud integrated DNS, and the inter cooperation between different systems is easily. So maybe we just pay attention on the authoritative, on the recursion resolver. But in the integrated cloud DNS, you must to make sure your data can be distributed to other clusters in different cloud and different regions. It must be security. So this is a challenge for the data distribution, and also need to make sure the resolution process. If you resolve a domain name from the cloud to the IDC resolvers, so in this link, there may be some hijacking, and there also may be, the data is isolated by the tenants. But if you resolve it in the cloud environment, you must make sure the data is truly isolated. Because there are many centralized DNS service. Actually, it's a central service. All the user data is stored in one node, so you must make them isolated. So I think this is, I just gave 2 examples, and I think there are more other security.
Okay, thank you.
Okay, any other questions? Let's check if any. What's up? Okay, it seems we don't have any questions. I am personally curious. You just mentioned about DOT and DOH, encrypted DNS. Do you have any ratios of traffic over encrypted DNS than traditional DNS in your system share?
Yeah, actually, in my presentation, I have said in the past 2 years, the security the queries has increased about 200 millions. Yeah, 200 million.
Okay.
But in all the queries, the security part is also small, I think. Yeah.
Okay. So okay, thank you. I think we're done with this part. Thank you, Mr. Ma. And finally, the last speaker will share from the angle of authorities in the DNS industry. We have Mr. Xuebiao Yuchi, a research fellow at CNNIC. His research interests include DNS and DNS abuse, and has published 1 Springer book and over 20 research papers. He also serves as a current member of ICANN CCNSO DNS Abuse Standing Committee. His talk today is about DNS abuse governance, challenges, and what to do next.
Hello, everyone. My name is Xuebiao Yuchi, coming from CNNIC, the registry .cn/ccTLD, and I'm happy to be here, and thanks for having me here. And my topic today will be mainly about the DNS abuse. The DNS abuse has been discussed extensively by the ICANN community. The DNS abuse could cause significant negative impact to the DNS and even the whole internet infrastructure. Unfortunately, they still have some fundamental issues that we have not addressed so well yet. Typically, what does DNS abuse exactly mean? How could we measure it properly? And how could we mitigate DNS abuse effectively? However, DNS abuse is so complex a problem, so no one could give us an explicit answer. So before we talk about these issues, let's look at some pictures first. The first one is a report published last year by the FBI Internet Crime Complaint Center. From the picture, we can see over the past 5 years, the center has received a total of over 3 million internet crime complaints, reporting a total loss of up to 30 billion in US dollars. And also, we could see the quality of victims together with economic losses are increasing year by year. Someone may ask, what does all this have to do with DNS abuse? Let's go ahead to see another picture from this report. In this picture, the report shows us the top 5 crime types comparison over the last 5 years. Note that DNS abuse is not tracked as a category here, but there does have categories of DNS abuse, which are tracked in this report, of which phishing is the top reported internet crime. And so we could infer from this picture that DNS abuse mitigation is essential for internet crime mitigation. Let's be more specific to look at some picture from ICANN's DAR project. The ICANN DAR project has been collecting DNS abuse related data and published monthly reports for several years. They also published a 4 years long report last year. From the DAR's monthly report data, we could see that the global percentage of abusive domain names as captured by DAR has been going up during the past year. However, we should keep in mind that the current DAR project are mainly focused on domain names in gTLDs rather than the ones in ccTLD. Besides these 2 reports, there are also many other reports focused either on internet crime or, to be more specific, on DNS abuse. These different reports indicate that when we are trying to capture DNS abuse trends in general, we should keep in mind that we would receive different answers depending on the question we asked and the data we used. No one could give us a complete and accurate answer. And the problem is always bigger than reported, and the exact size cannot be known forever. In fact, we still lack a common recognized definition of DNS abuse, although DNS abuse has been discussed extensively by the community. So what are we exactly talking about when we talk about DNS abuse? One of the main problem in the DNS abuse debate originates from its very definition. So it's not easy for the whole community to achieve consensus on DNS abuse definition. However, we could at least try to clarify some basic concepts regarding DNS abuse. First of all, DNS abuse versus domain name abuse. Usually, we treat these 2 terms the same in most cases. However, we should keep in mind that DNS abuse could actually mean a lot more than domain name abuse. Actually, all these misbehaviors, including DNS eavesdropping and DDoS attacks that could lead to negative impact to the DNS infrastructure, could all be treated as DNS abuse. However, since some of these misbehaviors could not be mitigated or interrupted by ICANN and ICANN community directly, so we have to narrow down the DNS abuse terms scope in this context. Although we have used the term DNS abuse here, we should keep in mind that when we are talking about the DNS abuse, we are actually talking about domain name abuse only, because the term DNS abuse could actually mean a lot more. The second issue is technical abuse versus content abuse. We usually divide DNS abuse into two categories, technical abuse and content abuse. It's important to recognize the distinctions between technical and content. Note that ICANN's mission is to preserve the security and the stability of the DNS infrastructure, but not intended or capable to be the internet content police. So ICANN only cares about technical abuse, which contains 5 types, namely malware, botnet, farming, phishing, and spam. And ICANN's contracted parties, namely the GTLD registrars and the registries, are only required explicitly to act against technical abuse. While these technical abuse are easy to do their judgment, things get to be more complicated when we face the content abuse problem. The lack of universal standards in content abuse is apparent. It turns out that something is illegal in one place, maybe not in another. So this is getting into quite a complicated area. The ICANN has clarified that its role do not extend to the regulation of content abuse, and ICANN does not have the capability to determine what content is legal or illegal. So efforts in content abuse mitigation are mainly made outside of ICANN. Unfortunately, there is an intrinsic difficulty in creating a clear division between technical and content abuse. And the clear-cut distinction between the technical and content abuse could be easily blurred in many practical scenarios. For example, phishing also involves malicious web content. A piece of malware might spread harmful content too. So at what level should DNS abuse be fought and prevented? Who is in charge for what? These are two of the most crucial questions in the DNS abuse mitigation debate. These limitations do not prevent ICANN or the community from taking steps to fight against DNS abuse. First, let's see efforts on DNS abuse from ICANN. For many years, ICANN has worked on a variety of issues related to DNS abuse. First is to contribute a trusted source of information by providing research, data, and expertise to help the community have fact-based discussions about the topic. For example, the ICANN STAR project has been facilitating the community's discussions and the policy makers very much by providing factual data and relevant reports in recent years. Second is to provide tools to the ICANN community. For example, bad actors may prefer to utilize some certain registrars to launch DNS abuse. These registrars might have low registration prices or specific payment methods, or they could offer free APIs for bulk registrations. So ICANN's InForSec project aims to systematically analyze the preferences attackers so as to conduct DNS abuse mitigation in a more proactive way. In addition, to identify those abusive domain names related to the COVID-19 pandemic or the Russia-Ukraine war, ICANN also launched the project called DNS TCR, which could provide well-evidenced reports of these related abuses to the sponsoring registrar who can take appropriate action. All right. Okay. Another important contribution by ICANN is to enforce contractual obligation with registries and registrars in DNS abuse mitigation. Over the past few years, ICANN has been working with registries and registrars of legacy TLDs on the proposed amendments to the base agreements, including RA and RAA, aiming to enhance the contracted parties' obligations in DNS abuse mitigation. We think this is a big step made by ICANN in DNS abuse mitigation among those JTLDs. Besides ICANN, several ICANN bylaw mandated review teams engaged further on the issue of DNS abuse, including 2 final reports from CCTIT and SSR2, both of which identified and reinforced the need for additional tools to help measure and combat DNS abuse. In the report issued by APAC, namely SEC 115, they called for a centralized abuse reporting tool, and we believe this idea could lead to significant change to our current DNS abuse reporting and handling procedure. In response to this report, a centralized abuse reporting tool named NetBeacon was presented during ICANN 74 last year by the DNS Abuse Institute, OPRR. It's a free centralized reporting tool currently for phishing, malware, botnet, and spam only. Aims to standardize and enrich DNS abuse complaints and distribute them automatically to related GTLD registrars. We also think this is a meaningful attempt to improve our DNS abuse reporting and handling procedure. Other important documental inputs include the contracted parties host that definition of DNS abuse in 2020 and the trusted notifier framework also by CPH in 2021. We think all these inputs are significant steps forward in framing the context of the roles, responsibilities, and capabilities of ICANN's contracted parties in DNS abuse mitigation. It's important to note that groups outside the community also contribute a lot to the topic of DNS abuse. For example, the Internet Jurisdiction Policy Network, who published the toolkit in 2021, trying to identify types of abuses that could be addressed at the DNS level, their corresponding thresholds for action, as well as the sequence of interaction between notifiers, registrars, and registries. And this handbook is also an important guideline for our DNS abuse handling. Other efforts include the DNS abuse framework, which is voluntarily launched in 2019. The framework explicitly pointing out that registrars and registries should act against technical abuse directly, as well as some particular forms of content abuse. And they also recognize that registrars and registries also have their own option against some particular forms of abuses. While voluntary frameworks like this are helpful, but they are not fully inclusive and have no incentive or penalty mechanism on these signed or unsigned parties, which could make themselves not so enforceable, however. A lot of work can also be found among these organizations like FIRST, APWG, and so on. You can even find some drafts and RFCs from the IETF, while I'm not going to give them too much detail here. Note that all these efforts mentioned above are mainly served for the GTLDs. The CCTLDs, however, are not subject to registry agreements with ICANN. So they are somewhat independent in their policy making in DNS abuse. However, unlike GTLDs, those CCTLDs are commonly owned by their local governments. Therefore, they are dependent on their government's oversight and have to subject to their local laws. As a result, CCTLDs are commonly taking much more strict measures against DNS abuse, especially for those content abuse. So to better understand the CCTLD's landscape when it comes to DNS abuse and to determine how to best serve CCTLDs, last year, CCNSO formed the DNS abuse standing committee. Note that the committee's purpose is not to share, is to share information, insights, and practices among CCTLDs, but not to formulate any policy or standards which is out of scope of the CCNSO policy remit. One interesting thing in last year, the committee launched a DNS abuse survey among the CCTLD. From the civil survey, we can easily see their diversity and independence of policy making in DNS abuse mitigation. So different CCTLDs are tackling with different types of content abuse. And they also admitted that that they are heavily dependent on their local government and subject to local laws. Most CCTLDs admitted that it is difficult for them to decide what is legal or illegal and which types of DNS abuse they should take action on. The answer is, as long as they receive an order from a competent authority who tell them that it's illegal, then they will take some action against it. Note that there are also some CCTLDs that are not handling DNS abuse so well. For example, the Freenom. The registry for 5 CCTLDs provides free domain name registration services and seals its customer's ID even after being used for illegal purposes. These 5 CCTLDs operated by Freenom has made up half of the top 10 TLDs most used by phishing. Last year, the Meta company initially filed a lawsuit against Freenom, alleging that the company failed to address complaints about phishing while monetizing traffic to these abusive domains. Then from the picture, we can see a considerable decline in phishing domains linked to Freenom's CCTLDs since the registrar was sued by Meta. However, we need to admit that the lawsuits have had little effect on the overall number of phishing domains, which have continued to rise in volume. If these free ccTLD phishing domains are closed down, then that might other ccTLDs more of a target. So from the above efforts made by different parties, we must recognize that DNS is an ecosystem, not just a registration system. All these parties can be involved and influenced by DNS abuse. And we also need to recognize that the limitation of each party. There's no single party who can address DNS abuse alone and perfectly. So we need the whole ecosystem's response. Different parties have different roles and responsibilities, as well as different options at hand to handle DNS abuse. So there's no one-size-fits-all solution. An effective approach by one party may not be effective for another. So what can we do next? The good news is that in cooperation with ICANN contracted parties and other groups within the community, the DNS ecosystem has been constructively engaged in developing common sense and practical efforts in DNS abuse mitigation. All parties within this community have their own parts to play in identifying, reporting, and mitigation DNS abuse within their respective roles and capabilities. It has been proved that the ICANN community has always been the best positioned that could bring the community together and give full play to all these players' potentials and initiatives. We admit that there still have a lot of work to be done, and we need to move forward with our community to make the DNS ecosystem more sustainable and reliable together. Thank you.
Okay, thank you. Let's check if there are any questions online. Not yet again. Okay, any questions from our on-site participants? Oh, okay. We have so Alexis, please unmute Jianchuan Zhang.
Hey, Xuebiao, thank you for sharing information. Jianchuan from ICANN Engagement Center in Beijing. So I'm ICANN staff. Thank you for sharing your observation. In particular, the ICANN community's efforts to mitigate DNS abuse. So my question is about, I understand that ccTLD is a little bit from gTLD. So ccTLD community might take their own, policies and approach within their own country. That's something different from the gTLD community. But my question is that, within the ICANN community, if there is a consensus policy, then all new gTLD registry will adopt that policy. Or if there is kind of policy, we can also change the registry agreement so that all gTLD registry operator can adopt that policy. But coming back to ccTLD community, do you see any efforts within the ccTLD community that there will be a consensus policy for CC so that all ccTLD operator will take the same policy or approach? Do you see any efforts within the CC community? Thank you.
Thanks, Ms. John. That's a good question. And And luckily, I'm just joined the CCNSO DNS Abuse Standing Committee last year, and I'm also a member of this committee. And last year, this committee launched a survey I just mentioned. So from the survey, you can see the CCTLD's efforts in DNS abuse mitigation is very diverse. And I realized that each of them are also very proud of their diversity in DNS abuse mitigation. So for your question, I think it's somewhat difficult for them to reach a consensus over the topic of DNS abuse mitigation, because there, as you have mentioned, there are RA and RAA between ICANN and the GTLD registry and the registrars, but actually there exists no agreement between ICANN and the CCTLDs. And actually, ICANN has no rights to intervene the CCTLD's oversight on their domain names. So I think it's somewhat difficult for those CCTLDs to reach consensus on this, but they can learn from each other to optimize their efforts in DNS abuse mitigation. But I think they are not willing to be told that they should do this, they should do that. I think it's not practical just now.
Okay. I also have one particularly interesting observation. You have cited from the ICANN DAR project, which reports the overall number and some analytics about domains put in abuse. And I noticed that there has been a rising trend in early 2023, a pretty sharp one. Does anybody have any analysis on what has been going on?
Yes, the DAR project actually published the report monthly, but this report are only faced to their contracted registrars and registries. Actually, only for registries so far. So next steps, they plan to open the report to the registrars, but till now the report is only faced to the registries. So you can visit their websites and find maybe you could find some data on this website
Okay.
and their reports. Yeah.
Okay, I'll check it out later. Okay, any other questions? Okay, seems no. So thank you, and our last speaker. So okay, so that's all we have for today. A quick recap of this session. We've talked about DNS operation challenges up on the cloud, and our speakers covered several topics, including service centralization of naked domains, attack against DNS load balancing, operating cloud DNS, and governance of internet domain abuse. I hope there have been inspiring moments for you all. At least there have been some myself. And before you leave, please note that the main event of ICANN APAC DNS Forum will take place in 2 weeks during July the 4th and July the 5th in Hong Kong, China. And we'll also have a readout session then, revisiting the highlights of all pre-event webinars, including today's. So do join us, and we hope to see you again in Hong Kong soon. Until then, take care, everybody.